There is a patch of sky above the constellation Fornax, roughly the apparent size of a grain of sand held at arm's length, in which there is nothing. No bright star, no smear of the Milky Way, no light at all that the naked eye can detect. For 30 years, astronomers pointed some of the most powerful instruments ever built at this nothing, and found everything. But Webb looked deeper, and what it found should not exist. How do you build a galaxy in less time than it takes the Earth to orbit the Sun 40 times? How does a universe still in its infancy produce the chemical fingerprints of old age? And why, the more precisely we measure the cosmos, the more violently it disagrees with the very equations that predicted it? In 1995, the director of the Space Telescope Science Institute made a decision that the scientific community greeted, initially, with outright hostility. Robert Williams had been allocated a portion of the Hubble Space Telescope's observing time for his personal use, a director's discretionary allocation, and he chose to spend it staring at an empty patch of sky for 10 days, not at a known galaxy cluster, not at a nebula of any renown, not at any object that had been catalogued, named, or suspected of being scientifically productive. He pointed Hubble at nothing for 10 days and he waited. The outrage was swift and genuine. Williams received letters from colleagues warning him that he was wasting irreplaceable telescope time on a cosmic void. He was told, in terms not always diplomatic, that the resulting image would be blank. Astronomers do not typically enjoy pointing their instruments at nothing. The opportunity cost was enormous. Every hour Hubble spent staring at an empty field was an hour not spent on active star-forming regions, nearby galaxies, or the exotic objects that justified the telescope's billion-dollar price tag. Williams held his ground. The image came back, and in that grain of sand sliver of sky, there were not 0 galaxies, not 1, not 10. There were approximately 3,000 galaxies, each one a full island universe of hundreds of billions of stars, packed into a field of view so small that a thumbnail held at arm's length would have covered it entirely. The image became known as the Hubble Deep Field. It transformed cosmology overnight and reframed humanity's understanding of its position in a universe that turned out to be almost incomprehensibly populated. This is where the story of the James Webb Space Telescope begins, not with Webb itself, but with the hunger that the Hubble Deep Field ignited. Because what the Deep Field showed astronomers was not the answer to any question. It was a door to an era of cosmic history that Hubble could barely glimpse and could never truly enter, because it lacked the tools to see what was there. The most distant objects in the Hubble Deep Field, the galaxies at the very edge of its reach, were smears, blurs, suggestions. They existed at a cosmic epoch so early their light had been stretched by the expansion of the universe from ultraviolet wavelengths all the way into the infrared, shifted so far toward the red end of the spectrum that Hubble's optical instruments could detect them only as ghost-like smudges in its most sensitive detectors. To truly see them, to see their structure, their chemistry, their size, you would need a telescope built not for visible light, but for infrared. You would need a telescope of an entirely different order of sensitivity and scale. You would need something like Webb. The James Webb Space Telescope was not built quickly. The concept that would eventually become Webb was first proposed in 1996, 1 year after the Hubble Deep Field photograph rewired the ambitions of the field. Its original projected cost was $500 million. Its actual cost, after more than 2 decades of engineering challenges, redesigns, political battles, near cancellation by the United States Congress, and a global pandemic, came to approximately $10 billion. The telescope that launched on Christmas Day 2021 was 25 years in the making, 10 times over budget, and represented the combined scientific labour of more than 10 Zuzan engineers, astronomers and technicians across 17 nations. It carries the name of James E. Webb, who served as NASA administrator during the Apollo era, a fitting tribute perhaps, because both missions shared the character of reaching for something that many people believed was technically impossible. Webb's primary mirror is 6.5 meters across. This is not merely an incremental improvement on Hubble's 2.4-meter mirror, it is a transformation. The light collecting area of Webb's mirror, the total surface area available to gather photons from the distant universe, is 25.4 square meters compared to Hubble's 4.5 square meters. Webb collects roughly 5.6 times more light than Hubble per unit time. But raw mirror size tells only part of the story. Webb was engineered to observe in the near-infrared and mid-infrared portions of the electromagnetic spectrum, wavelengths ranging from 0.6 to 28 micrometers. This matters because of a phenomenon called cosmological redshift. As the universe expands, the wavelengths of light travelling through it are stretched proportionally to the distance they have travelled. A galaxy that existed 13 billion years ago and emitted ultraviolet light has, by the time that light arrives at our detectors, had its wavelength stretched by a factor of more than 8. That ultraviolet photon arrives as an infrared photon. Hubble cannot effectively detect it. Webb was built specifically to catch it. To detect those faint infrared signals, Webb's instruments must be kept extraordinarily cold. Cold enough that the telescope itself does not outshine the objects it is trying to observe through its own thermal emission. The solution was a sun shield the sizes of a tennis court, a 5-layer membrane of aluminized Kapton film that keeps the instruments operating at -233 degrees Celsius, just 40 degrees above absolute zero. Webb carries no rocket that could power a flight to a cool, shadowed orbit around Earth. Instead, it travels to the second Lagrange point, known as L2, a gravitational equilibrium point approximately 1.5 million kilometers from Earth in the direction directly away from the Sun. At L2, the gravitational pulls of the Earth and the Sun combine with the centrifugal effect of orbit to hold a spacecraft in a stable position where the Sun, Earth and Moon are always on the same side of the sky. The sun shield can therefore always be kept between Webb and any source of warmth. The result is a cold, stable platform for instruments of almost unimaginable sensitivity. Instruments capable of detecting the infrared light of a galaxy that formed when the universe was less than 300 million years old. When Webb launched, scientists worldwide held their collective breath through a deployment sequence of 344 individual steps, each one a potential single point of failure. No previous telescope had required anything remotely like it, but it worked, every step. And when the first images were released in July of 2022, the reaction from the global scientific community was not merely awe, it was in many cases profound unease, because Webb was not just showing us what we had expected to see in greater detail. It was showing us things that, according to our best models, should not be there at all. That is where this story truly begins. Not with launch, and not with celebration. With the moment the data arrived and the theorists went quiet. There is a concept in cosmology called the hierarchical model of galaxy formation, and for roughly 4 decades it has been the bedrock of our understanding of how structure emerged in the early universe. The model is elegant and well supported, or rather it was well supported. Its logic runs as follows. After the Big Bang, the universe consisted of hydrogen, helium, and a web of invisible dark matter, whose gravitational influence would eventually guide the formation of everything visible. In the earliest epochs, the density fluctuations in this dark matter web were small. Gravity pulled matter together slowly, first into small clumps, miniature proto-galaxies called halos, which then merged over hundreds of millions and billions of years to build progressively larger structures. Large galaxies, under this framework, are the product of time. They require mergers, accretion, extended periods of star formation, the recycling of stellar material through generations of supernova explosions. You cannot build a massive, chemically mature galaxy quickly, because the ingredients that massive galaxies contain, heavy elements like oxygen, carbon, silicon, iron, can only be forged inside stars and scattered into the interstellar medium through those stars' deaths. This takes generations, this takes time, and in the first 300 to 500 million years after the Big Bang, the universe had almost no time at all. This is what the models predicted. This is what decades of computer simulations, incorporating everything known about gravity, dark matter, hydrodynamics, and stellar evolution, converged upon. The early universe was supposed to be a sparse, primal environment, a nursery of the simplest structures, just beginning the long work of building the cosmos we inhabit today. Then Webb looked. The first hint of trouble came with the early photometric results. The initial survey images, taken before full spectroscopic confirmation was available. Photometric redshift estimation works by comparing the relative brightness of an object across multiple filters. The Lyman break, the sharp cutoff in light at wavelengths shorter than 91.2 nanometers, where neutral hydrogen absorbs virtually all photons, shifts predictably with redshift. And by identifying this break across multiple filter bands, astronomers can estimate how far away a galaxy is without yet taking its spectrum. Within weeks of Webb's first science observations, the photometric catalogues began filling with objects at redshifts that nobody had expected. Not in that abundance, not at that brightness, and not with those apparent sizes. The normal expectation, derived from every pre-JWST simulation and extrapolation, was that galaxies at redshifts above 10, corresponding to a universe younger than 500 million years old, would be extraordinarily rare, small, faint, perhaps detectable in the deepest fields as single-pixel smears, if at all. What Webb was finding instead were galaxies at redshift 10 that were luminous, galaxies at redshift 12 that appeared, by every photometric indicator, to contain substantial stellar mass. And then, the data point that stopped people mid-sentence, candidates at redshift 15 and beyond, placing them in a universe barely 300 million years old, with UV luminosities that defied every extrapolation of the standard model. In 2023, the astronomer Mike Boylan-Colchin at the University of Texas published a paper in Nature Astronomy that put the problem in the starkest possible terms. Boylan-Colchin is not given to hyperbole. He is a theorist of precise, disciplined habits of expression, and his paper was notable precisely for the controlled urgency beneath its technical language. What he demonstrated was that even taking the most optimistic assumptions about the efficiency with which the early universe could convert gas into stars, assuming essentially that every single atom of baryonic matter that fell into a dark matter halo immediately became a star with perfect efficiency, wasting nothing to heating, outflows, or feedback. The predicted stellar masses of galaxies in the first 500 million years still fell dramatically short of what Webb was appearing to see. This is the early galaxy mass problem, and it is not a small discrepancy. In standard cosmological models, star formation efficiency in the early universe was expected to be modest. Perhaps a few percent of available baryonic matter converted into stars per freefall time, limited by feedback from supernovae and radiation pressure from hot young stars, even allowing efficiency to reach the theoretical maximum of 100%, a physically impossible scenario. Some of Webb's candidate massive early galaxies were appearing to approach the total baryonic mass budget that the dark matter halos containing them could plausibly have accumulated, not 10% over budget, not double. The most extreme candidates appeared, if the initial photometric mass estimates were correct, to be near or at the theoretical upper ceiling of what any galaxy could contain. The phrase that circulated in seminars and preprint discussions in the months following these early results was measured but remarkable: in tension with the standard model. In the language of physics, intention is an understated expression of serious concern. The standard cosmological model, known formally as lambda CDM, for lambda cold dark matter, had survived 3 decades of observational tests, from the cosmic microwave background measurements of the WMAP and Planck satellites to the large-scale structure surveys that mapped hundreds of millions of galaxies. It was not a fragile theory. It had earned its central position through a series of spectacular predictive successes, and now a telescope that had been operating for less than a year was producing data points that sat uncomfortably outside its predictions. Not everyone was alarmed. Several prominent cosmologists counselled patience. The photometric redshift technique, for all its utility, carries substantial uncertainties. A galaxy at very high redshift could be mimicked by a galaxy at much lower redshift with unusual spectral energy distribution, a so-called interloper. The mass estimates derived from photometry alone rested on assumptions about stellar populations, initial mass functions and dust attenuations that could all be wrong in ways that would reduce the inferred stellar masses. The proper response, the more cautious voices argued, was to wait for spectroscopic confirmation, for the direct measurement of spectral lines that would pin down redshifts with precision and render the debate no longer a matter of photometric inference. A spectroscopic confirmation campaign began, and that is when things got genuinely complicated. Within the JWST program, the JWST Advanced Deep Extragalactic Survey, a 770-hour observing campaign led by a consortium of astronomers from institutions across North America and Europe. The team began taking spectra of the highest redshift candidates with Webb's near-infrared spectrograph, known as NIRSpec. The NIRSpec instrument can take spectra of up to 100 objects simultaneously using a microshutter assembly, a remarkable grid of 250,000 individually addressable microscopic doors that can be opened and closed to select which points of light in a field of view are allowed to enter the spectrograph. It is, in the history of astronomical instrumentation, one of the most complex detectors ever flown. The spectra came back, and instead of revealing that the early photometric results had been overstated, instead of showing that the most extreme candidates were actually lower redshift interlopers, the spectra confirmed the candidates and then exceeded them. Galaxies that photometry had placed at redshift 12 were spectroscopically confirmed at redshift 12. The photometric estimates had not been dramatically wrong, and when the team focused NIRSpec on the most exceptional candidate in the DZS field, a galaxy catalogued as JWST 14-0, what came back was a redshift of 1432, making it the most distant galaxy ever spectroscopically confirmed by a substantial margin. A redshift of 14.32 corresponds to a universe 290 million years old. The Big Bang occurred 13.8 billion years ago. JWST 14-0 existed when the universe was barely 2% of its current age. Its light has been travelling to us for 13.5 billion years. But the redshift was not the most confronting aspect of the discovery. The galaxy's size and luminosity were. JWST 14-0 has a half-light radius of approximately 260 parsecs. It is physically extended across a region of space roughly 850 light-years across. This is not the pinprick of a compact proto-galaxy just beginning to assemble. It is a spatially extended system, large enough that the team could rule out a dominant contribution from an active galactic nucleus. A central black hole whose radiation might otherwise explain the galaxy's exceptional brightness. The UV luminosity is equivalent to MUV of -20.81, making it the third most UV luminous galaxy among the entire population of 700 redshift greater than 8 candidates in the JWST catalogue. Despite being the most distant of them all, something built a bright, extended, massive galaxy in less than 290 million years. The models had not seen this coming, and the question that followed, a question that, as of mid-2026, remains open, is whether this is a surprise that the standard model can absorb, or a crack in the foundation deep enough to bring down the whole structure. Here is a chemical fact that, once you understand it, makes the discovery of JWST 14-0 considerably more disturbing. Oxygen is not a primordial element. The Big Bang produced hydrogen, helium, and vanishingly small traces of lithium. That is the full chemical inventory of the young universe. Everything else on the periodic table, every carbon atom in every DNA molecule, every iron atom in every red blood cell, every oxygen atom in every breath you have ever drawn, was forged inside stars. Not the first generation of stars, not even the second. Oxygen is produced in the CNO cycle and in the triple alpha process inside intermediate and massive stars. scattered into the interstellar medium when those stars end their lives in supernova explosions, incorporated into the dust and gas clouds from which the next generation of stars and planets forms. To produce detectable quantities of oxygen in a galaxy, you do not merely need the first stars to have formed. You need the first stars to have formed, lived their full stellar lives, which even for the most massive and fastest burning stars takes at minimum a few million years, and died in supernovae that distributed their heavy element yields into the surrounding gas. You then need that enriched gas to have been incorporated into subsequent generations of star formation. This is a multi-step, multi-generation process, and in a galaxy that existed only 290 million years after the Big Bang, a galaxy whose stellar population must therefore have begun forming at redshift 20 or higher when the universe was less than 200 million years old. The presence of substantial oxygen is what the senior author of the JWST study, George Reek of the University of Arizona, described publicly as genuinely mind-boggling. The MIRI instrument, the mid-infrared instrument aboard Webb, detected the signatures of this oxygen through infrared emission lines at wavelengths shifted to 7 micrometers in the observer's frame. This required 43 hours of MIRI integration time alone, along with 167 hours of NIRCam imaging. A total of approximately 9 days of observing time concentrated on a patch of sky that lead researcher Jakob Helton described by holding up a grain of sand at arm's length. If the telescope had been pointed even a fraction of a degree in any other direction, Helton noted, they would have missed the MIRI data entirely. The galaxy happened to fall in the narrow region of sky where MIRI could provide its critical contribution. The oxygen detection was later independently confirmed by ALMA, the Atacama Large Millimeter-SOP-Millimeter Array in Chile, which detected the O3 emission line at 88 micrometers, redshifted to the millimeter regime. Two independent telescopes, using completely different instrumental techniques, both finding oxygen in a galaxy that formed when the universe had barely existed. This is not a measurement artifact. This is real. This is the JADES GSE 14-0 problem. A galaxy existed at a cosmic epoch when, by every prior model, the universe was too young to have built it. And it wasn't merely present, it was chemically evolved, spatially extended, and brilliantly luminous. The standard hierarchical model does not have a natural explanation for this. And JWST GSZ 40 is not alone. The JWST survey alone has identified more than 700 galaxy candidates at redshift greater than 8, and the number density of bright galaxies at these early epochs is more than 10 times higher than pre-JWST extrapolations predicted. But as startling as the galaxy formation problem is, it is not the only crisis Webb has either created or deepened. There is a second, entirely independent problem, one that predates Webb, but that Webb's measurements have made considerably sharper, considerably harder to dismiss, and considerably more alarming for the future of the standard cosmological model. It is called the Hubble tension, and it is the kind of problem that keeps cosmologists awake in the small hours of the morning. The Hubble constant, denoted h0, is the rate at which the universe is expanding. It describes how fast galaxies are receding from each other per unit of distance. A larger h0 means faster expansion, a smaller h0 means slower. The modern value of the Hubble constant can be measured in two fundamentally different ways, and this is where the problem begins. The first method uses the cosmic microwave background, the faint afterglow of the Big Bang, imprinted on the sky when the universe was approximately 380,000 years old, to fit a complete cosmological model and extrapolate forward to the present-day expansion rate. The Planck satellite measured the CMB with extraordinary precision and returned H067.4 plus MOS 0.5 km per second per megaparsec. This is a clean, well-understood measurement. The second method uses the cosmic distance ladder, a chain of overlapping distance measurements using Cepheid variable stars, Type Ia supernovae, and other standard candles, to measure how fast nearby galaxies are actually receding today. The most prominent group working on this method, led by Nobel laureate Adam Riess of Johns Hopkins University, has returned a value of H0 73 km per second per megaparsec, give or take approximately 1. These two numbers disagree by approximately 5.5 km per second per megaparsec. This may sound like a small discrepancy, but in a well-understood physical system, it is not. The statistical significance of the disagreement reached 5 sigma, a level at which, in any other branch of physics, one would be compelled to conclude that something is genuinely wrong with either one of the measurements, or with the model connecting them. In particle physics, 5 sigma is the standard threshold for declaring a discovery. In cosmology, 5 sigma of tension between two independent datasets is, functionally, a crisis. The Hubble tension was present before Webb. But Webb was expected, by much of the community, to resolve it, to provide independent infrared measurements of the Cepheid distance ladder that would either confirm or correct the existing local measurements. If Webb showed that systematic errors in the Hubble Space Telescope's Cepheid measurements, perhaps arising from Hubble's limited infrared sensitivity, causing crowding effects in dense stellar fields, had inflated the local H0 value, then the tension would dissolve. The standard model would be saved. This did not happen. Webb's measurements of Cepheid distances, published in late 2024, confirmed the Hubble Space Telescope's Cepheid results. The local expansion rate is genuinely high. The tension did not dissolve. A May 2025 study combining Webb and Hubble data yielded H070, 4 km/s NOPP with a 3% uncertainty, still intermediate between the two incompatible values and still inconsistent with the Planck CMB value at several sigma. Wendy Friedman of the University of Chicago Carnegie Hubble program has pursued alternative distance ladder methods, using the tip of the red giant branch rather than Cepheids, argued in 2025 that her methodology reduces the tension, but even her revised values sit uncomfortably between the two camps, satisfying neither. The honest summary is this: the Hubble tension is real. After Webb, there is no plausible systematic measurement error that could explain it. That leaves only 2 possibilities, and both are profound. Either one of the cosmological measurement pipelines has an unidentified systematic error that is somehow escaping detection in multiple independent analyses using multiple independent methods, or the standard cosmological model, lambda CDM, is incomplete. Perhaps the physics of the early universe was different in a way that alters the CMB-derived expansion rate prediction. Perhaps dark energy is not the simple cosmological constant Einstein assumed, but something that evolves over time, changing the expansion history in ways that affect the inferred H0. Perhaps there is a fundamental assumption buried in the model about the equation of state of dark energy, about the behavior of neutrinos, about the properties of dark matter, that needs to be revised. And then, as if 2 separate crises were insufficient, Webb added a third. Beginning in March 2024, reports began emerging from multiple independent survey programs of a new class of object in the early universe: faint, compact, extraordinarily red point sources appearing throughout every deep field Webb examined. They were not in any pre-Webb catalogue. They had no clear counterparts in existing photometric datasets, and they defied clean classification into any known category. Researchers began calling them little red dots. By late 2024, the community had accumulated enough data on the little red dots to know several things. They exist at redshifts typically between 3 and 9, corresponding to cosmic epochs between roughly 700 million and 2 billion years after the Big Bang. They show broad hydrogen emission lines consistent with fast-moving gas in the vicinity of an actively accreting massive black hole, and they appear to be overwhelmingly common. Their number density in the early universe substantially exceeds the predictions of any model for the population of active galactic nuclei at these epochs. The broad line regions imply black holes of 100 million to several billion solar masses. But these black holes appear, in many cases, to be dramatically more massive than their host galaxies can plausibly contain under normal galaxy-to-black hole scaling relations derived from the local universe. This is the little red dot problem. A black hole is supposed to grow alongside its host galaxy, its mass constrained to a narrow fraction of the host's total stellar mass by feedback processes. The black hole's radiation blowing away the very gas that would otherwise feed both the black hole and further star formation. In the local universe, the black hole mass is typically approximately 0.1 to 0.5% of the host galaxy's bulge mass. In several of the little red dots, the black hole appears to contain a mass comparable to, or in some cases exceeding, the inferred stellar mass of the entire host. They are, as the literature has begun calling them, overmassive. One by one, like pressure points on a structure under load, these problems were accumulating. The too massive early galaxies, the too fast expansion rate, the overmassive black holes in the little red dots, 3 independent anomalies from 3 independent datasets, pointing toward the same unsettling conclusion: the standard model of cosmology, one of the most precisely tested physical theories in the history of science, may be missing something fundamental. What was it missing? That question would take Webb, and the people behind it, down a road more complicated than any of them had anticipated. To understand what Webb may be dismantling, it is necessary first to understand what it is. The lambda CDM model, lambda standing for the cosmological constant, CDM for cold dark matter, is not a speculative hypothesis. It is the distilled product of 5 decades of cosmological observation and theoretical development, and it is arguably the most successful scientific framework ever constructed for describing the large-scale structure of the universe. To appreciate why its potential failure would be so significant, you need to understand both how it works and how spectacularly well it has worked. The lambda part of the name refers to the cosmological constant, the symbol lambda, originally introduced by Albert Einstein in 1917 to counteract the gravitational collapse implied by his field equations and make them compatible with what he believed, incorrectly, to be a static universe. Einstein famously abandoned lambda after Edwin Hubble's observations confirmed that the universe was expanding. He is reported to have called it his greatest blunder. But lambda returned in 1998 when 2 independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, discovered, through careful measurements of Type Ia supernovae at high redshift, that the universe's expansion was not slowing down as gravitational attraction would demand, but was in fact accelerating. The only way to explain this acceleration within general relativity was to reintroduce a term equivalent to Einstein's cosmological constant, a form of energy intrinsic to space itself, now called dark energy, which exerts a repulsive gravitational effect and drives the universe apart at an accelerating rate. The leaders of both supernova teams shared the 2011 Nobel Prize in Physics for this discovery. Dark energy, in the lambda CDM framework, accounts for approximately 68% of the total energy content of the universe. The CDM part refers to cold dark matter, a hypothetical form of matter that does not interact electromagnetically. It cannot emit, absorb, or reflect light, interacts only gravitationally and possibly through the weak nuclear force, and moves slowly, cold, compared to the speed of light. Dark matter accounts for approximately 27% of the universe's total energy content. The baryonic matter of which stars, planets, gas, dust, and human beings are made accounts for the remaining 5%. The universe is, by this accounting, 95% composed of things we cannot directly detect, cannot directly measure, and do not fully understand. Together, lambda and CDM form a scaffold. The dark matter provides the gravitational skeleton, the cosmic web of filaments, sheets, and nodes along which baryonic matter flows and accumulates to form galaxies. The dark energy determines the large-scale expansion history, the rate at which space itself stretches, diluting matter, changing the distances between galaxy clusters, and ultimately governing the fate of everything. Within this framework, the growth of structure, the emergence of galaxies, clusters, and the cosmic web from the initially nearly uniform post-Big Bang universe is governed by well-defined equations that can be simulated on supercomputers with increasing fidelity, and for decades, lambda CDM produced predictions that matched observations with extraordinary precision. The temperature fluctuations in the cosmic microwave background, mapped first by the COBE satellite, then by WMAP, then by Planck, fit the lambda CDM predictions to better than 1%. The large-scale distribution of galaxies, the baryon acoustic oscillation scale, the shape of the matter-power spectrum, matched simulations with exquisite fidelity. The abundances of light elements produced in the first 3 minutes after the Big Bang, the helium fraction, the deuterium to hydrogen ratio, agreed with the theoretical predictions of Big Bang nucleosynthesis threaded through the lambda CDM framework. By the early 2000s, lambda CDM had achieved the status of mature, confident, tested physical theory. Its critics were in the minority, and many of their alternative proposals had been observationally eliminated. This is why Webb's findings matter so much, and why the language of tension and crisis in the cosmological community deserves to be taken seriously rather than dismissed as scientists manufacturing excitement over minor discrepancies. When a model has survived as many tests as lambda CDM has, a single anomalous result can be confidently attributed to measurement error. 2 independent anomalies warrant serious scrutiny. 3 independent anomalies, particularly when they arise from a new instrument operating in a previously inaccessible observational regime, and when they all point in the same general direction of the early universe was more complex, more structured, and more active than predicted, constitute a genuine scientific crisis. Not a crisis in the sense of a field dissolving into chaos, but a crisis in the original Greek sense, a critical turning point that demands resolution. What are the proposed explanations? There are several serious contenders, and their diversity reflects both the creativity of the theoretical community and the depth of the problem. The first and most conservative class of explanations holds that lambda CDM is correct, but that our models of the baryonic physics within the lambda CDM framework are incomplete. Star formation efficiency in the standard simulations is suppressed by feedback, by the radiation and stellar winds from hot young stars, and by supernova explosions, which heat and disrupt the gas from which new stars would otherwise form. If this feedback were somehow less effective in the early universe, if, for instance, the first generation of stars produced less feedback per unit mass, or if the very dense gas in early galaxies was less susceptible to disruption, then galaxies could build up stellar mass more rapidly without requiring any change to the fundamental cosmological model. This is sometimes called the bursty star formation hypothesis. The idea that early galaxies underwent episodes of extremely intense, highly efficient star formation on short timescales, punctuated by phases of suppression, and that Webb is catching these galaxies in their burst phases when they appear unusually bright and massive. The bursty star formation hypothesis has genuine theoretical support. Simulations, including more realistic treatments of the interstellar medium, supernova feedback, and radiation pressure, have shown that early galaxies can indeed undergo episodic bursts of star formation that make them temporarily much more UV luminous than their time-averaged star formation rates would suggest. Some researchers have argued that this effect, combined with revisions to the assumed dust content of early galaxies, which affects how much of their UV light escapes to be detected by Webb, is sufficient to reconcile the observed galaxy number counts with lambda CDM. This argument was strengthened in early 2025, when a team at NASA released a paper titled "Webb finds early galaxies weren't too big for their britches after all." Their analysis, using improved stellar population modelling techniques, found that when more careful treatment of nebular emission was applied to the spectral energy distributions of early galaxies, accounting for the contribution of hot gas in star-forming regions to the overall brightness, the inferred stellar masses came down significantly. The most extreme photometric mass estimates, the ones that had generated the most alarm in 2022 and 2023, turned out to be partially inflated by the contribution of nebular continuum emission to the apparent stellar light. the more accurate spectroscopic stellar masses, derived once NIRSpec data was available, were in many cases more modest. Some researchers concluded from this that lambda CDM was not in serious trouble, only that the baryonic physics in the simulations needed refinement. But here is where I find myself genuinely conflicted about the measured reassurance of that conclusion, because the spectroscopic campaign did not reduce the anomaly to zero. JWST GSZ14-0, with its spectroscopically confirmed redshift of 1432 and its measured oxygen abundance, was not explained away by improved stellar population modelling. Its stellar mass, even after the most conservative revisions, remains extraordinary for a galaxy formed in the first 290 million years of cosmic history. The number density of bright galaxies at redshift above 10 remains, by a factor of 10, higher than pre-JWST predictions, and the bursty star formation hypothesis, while potentially explaining the UV luminosity excess, does not naturally produce the chemical enrichment, the oxygen, that Myrie and Alma detected in JWST GSZ14-0. That oxygen requires real stellar evolution, real supernovae, real chemical enrichment. You cannot burst your way to a high oxygen abundance in 290 million years without having already accomplished multiple generations of star formation, which pushes the complication only further back in time, toward an epoch when even the bursty model struggles to explain what was happening. The second class of explanations is more radical and involves revisions to the dark matter paradigm. If dark matter has properties different from the simple cold, collisionless particle assumed in lambda CDM, the growth of structure in the early universe could differ from standard predictions in ways that accelerate galaxy formation. Warm dark matter, in which dark matter particles have non-negligible velocities, suppresses small-scale structure formation in ways that could affect early galaxy mass functions. Fuzzy dark matter, in which dark matter consists of ultralight axion-like particles with de Broglie wavelengths on the scale of kiloparsecs, smooth out structure on sub-kiloparsec scales in ways that some researchers believe might address certain persistent small-scale tensions in the lambda CDM model. Self-interacting dark matter would change the density profiles of dark matter halos in ways that affect galaxy formation in the central regions. None of these alternatives has yet made a definitive observational case, but none of them has been definitively excluded by Webb's data either. The third and most consequential class of explanations involves revisions not to dark matter but to dark energy. This is where the Hubble tension and the galaxy formation problem begin to speak to each other. The cosmological constant lambda has a specific property. Its energy density does not change as the universe expands. It is a fixed property of the vacuum of spacetime. But if dark energy is not a cosmological constant, if it is instead a dynamic field whose energy density evolves with time, then the expansion history of the universe would differ from the lambda CDM prediction in ways that could affect both the inferred Hubble constant and the predicted rate of galaxy formation in the early universe. In 2025, results from the Dark Energy Spectroscopic Instrument, DESI, provided the strongest evidence yet that dark energy may be evolving. The DESI survey, which measured the clustering of 57 million galaxies across a range of cosmic epochs, found that the best fit equation of state for dark energy was inconsistent with the constant value of -1 predicted by the cosmological constant at a level of statistical significance between 2.5 and 3.9 sigma, depending on the analysis method and dataset combination. The parameter W0, describing the present-day equation of state of dark energy, came out more negative than -1, while the parameter WA, describing its rate of change with scale factor, suggested that dark energy was less dominant in the past than it is today. If true, this would mean that the universe's expansion history was different at early times than lambda CDM predicts, and that the CMB-derived value of H0, which depends critically on the assumed expansion history, may be systematically biased. The DESI results were not definitive. 3 sigma is suggestive, not conclusive. The collaboration itself was careful to note that systematic errors, particularly in the modelling of galaxy bias and the treatment of the baryon acoustic oscillation feature, could potentially contribute to the anomalous signal. But the direction of the anomaly was consistent with what would be needed to simultaneously resolve both the Hubble tension and moderate aspects of the early galaxy formation problem. And when you have two independent experiments, DESI's galaxy clustering measurements and Webb's early galaxy observations, both pointing in the same direction of anomaly with respect to the standard model, the probability of a coincidental double measurement error becomes increasingly uncomfortable to invoke. There is a fourth explanation. It is the one that some physicists entertain privately and hesitate to publish. The explanation that involves not a modification to the model's parameters or baryonic physics, but a structural revision to the framework itself. Lambda CDM assumes that general relativity is the correct description of gravity on cosmological scales. There is no observational proof that this is true. General relativity has been tested with extraordinary precision in the solar system, in binary pulsar systems, and in the strong field regime near black holes, but its behaviour on scales of hundreds of megaparsecs and above, the scales on which the Hubble constant is measured, and on which the large-scale structure of the universe is determined, has never been independently tested to the same precision. If gravity deviates from general relativity on those scales, if, as some modified gravity theories propose, there are screening mechanisms or scale-dependent modifications to Newton's constant, then both the galaxy formation timeline and the expansion rate could be affected in ways that current models do not capture. I will be transparent about my own view on this. I think the most likely resolution to Webb's challenges to lambda CDM will turn out to be a combination of improved baryonic physics modelling and modest revisions to the dark energy equation of state, not a complete overthrow of the framework. The standard model has survived too many tests with too much precision to be wholly wrong, but I am equally sure that the version of lambda CDM that we will be using in 50 years will look different from the one we use today, and that the differences will trace directly back to the data that Webb has gathered and is continuing to gather. The question is not whether the model needs revision. It clearly does. The question is how deep the revision needs to go. That question was made more urgent and considerably more human by the story of one particular team working on one particular patch of sky on one particular night in October 2023 when the data started coming in and nobody left the telescope queue to go home. Kevin Heinlein did not sleep well in the autumn of 2023. This is a fact he has shared in interviews without any particular complaint. The sleeplessness was not an affliction, but a symptom of the specific electric anxiety that descends on astronomers when data from a major observing campaign begins to arrive, and the question of what you are going to find is no longer theoretical. The NARCam images were coming in from the JWST Origins Field program, the deepest imaging campaign in Webb's still young history at that point, and Heinlein's role in the collaboration placed him at the intersection of the photometric analysis pipeline and the spectroscopic follow-up queue. He was, in the specific language of the data workflow, one of the first people to see what the telescope had found. The JWST collaboration was not a small enterprise. It involved more than 80 astronomers distributed across institutions in the United States, Europe, and beyond. From the Space Telescope Science Institute in Baltimore to Cambridge, from the University of Arizona's Steward Observatory to institutions in Bologna and Edinburgh. The survey had been allocated 770 hours of Webb's precious observing time, spread across multiple observing programs, targeting two of the most heavily studied fields in the sky. South and north, the same regions that had hosted the original Hubble Deep Field and its successors for 3 decades. The logic of targeting these fields again was straightforward. The pre-existing multi-wavelength data from Hubble, Spitzer, Chandra, and ground-based telescopes would provide crucial context for interpreting whatever Webb found. But the team knew going in that they were not merely filling in blanks left by Hubble. They were opening a door. Heinlein's specific expertise is in galaxy spectroscopy, the art of pulling chemical and physical information out of the spread of wavelengths that a galaxy emits. He had been involved in building the photometric selection criteria for JWST candidates before the first observation, helping to define the filter combinations and colour cuts that would identify the highest redshift galaxies among the thousands of objects in each field. This kind of preparatory work is unglamorous and underappreciated. It is the astronomical equivalent of designing the expedition before you leave base camp, and it requires particular combination of statistical rigour and physical intuition, because the selection criteria you build in advance determine, to a large degree, what you will and won't find. A selection criterion designed too conservatively will miss the most extreme objects. Designed too aggressively, it will fill your observing queue with contaminants that waste spectroscopic time. In early 2023, when Heinlein's team was refining the photometric catalogue for the JWST, the JWST Origins field, a smaller, deeper subset of the D near South field that would receive the very deepest web imaging, there was one object that kept producing anomalous results in the selection pipeline. It appeared, by its photometric redshift probability distribution, to be at very high redshift 14 or above, but it had a problem. It was sitting only 0.4 arcseconds away from a known foreground galaxy at redshift 3.475, and the proximity of that foreground galaxies meant its photometric analysis was complicated by contamination. The preliminary assessment was cautious. The object was flagged as a low redshift interloper candidate. It was possible, the team noted in their catalogue paper, that the apparent photometric break was caused not by the Lyman alpha break of a high redshift source, but by the Balmer break of the foreground galaxy at redshift 3.475, whose Balmer break sits at a wavelength that is spectrally similar in the observed frame to the Lyman break at redshift 14. The two signals were confusable. The galaxy was tentatively set aside. It was this caution, this willingness to doubt the most extraordinary candidate, that makes what happened next in the spectroscopic campaign so remarkable. When the NIRSpec multi-object spectroscopy observations were being planned for the JWST, the question of whether to include the ambiguous object in the list was debated. Including it cost real observing time. If it turned out to be the low redshift interloper that the conservative reading of the photometry suggested, that time would be wasted. But the optimistic reading of the photometry, the probability that it was genuinely at redshift 14, was not negligible. The team decided to include it. The NIRSpec spectra arrived. Heinlein was among the first to process them, and what the data showed was this: the object was real. The sharp break in the spectrum at 1.85 micrometers was a Lyman alpha break, not a Balmer break. The foreground galaxy's spectrum was independently measured, confirming it was at redshift 3.475, and the wavelength discrepancy between the two potential break features was large enough, once the foreground galaxy's contamination was properly subtracted, to exclude the low redshift interpretation. The distant object was at redshift 1432. The light from JWST GSZ 14.0 had left its source when the universe was 290 million years old, and it had just arrived at a detector 6, 5 meters across, floating in space 1.5 million kilometers from Earth. After a journey of 13.5 billion years, Jacob Helton, a graduate student at the University of Arizona, who served as lead author on the subsequent Nature Astronomy paper, describing JWST GSZ 14-0's chemical properties, has described the experience of working on this galaxy as one of the most intellectually destabilizing of his career, and he had spent that career expecting to be surprised. The chemical complexity was what broke his composure. The MIRI data arrived over several weeks, processed through a pipeline calibrated for an instrument that was itself only a year old, and when the team ran the spectral energy distribution modelling, fitting models to the multi-wavelength photometry to extract the galaxy's physical properties, the oxygen abundance signal emerged with a statistical robustness that resisted all attempts to explain it away. The fact that we found this galaxy in a tiny region of the sky means that there should be more of these out there, Helton said in the public announcement. The statement was scientifically careful, calibrated, accurate, but read against the context of what the discovery implied, read against the knowledge that this galaxy had accomplished multiple generations of stellar evolution, had produced oxygen abundances comparable to those seen in local galaxies, had built a stellar mass of approximately 500 million solar masses, all within 290 million years of the Big Bang. It carried an unmistakable undercurrent of genuine wonder, and something closer to vertigo. George Reek, the Regents Professor of Astronomy at the University of Arizona, who served as the study's senior author, and whose decades-long involvement in infrared astronomy had made the MIRI instrument possible, was more direct. It's a very complicated cycle to get as much oxygen as this galaxy has, he said in the announcement. So it is genuinely mind-boggling. Reek had been building infrared astronomical instruments since the late 1960s, and he had waited his entire career for a telescope sensitive enough to do what MIRI was now doing. The discovery of oxygen in JWST 14.0 was not just a scientific result for him. It was the validation of a multi-generational investment, a confirmation that the decades spent designing, advocating for, building and calibrating increasingly sensitive infrared detectors had, in the end, been pointed at a sky that rewarded the effort in a way that exceeded the most optimistic ambitions of anyone involved. The observation that made the MIRI detection possible deserves its own pause. The total observing time for the NIRCam component of the JWST Origins field was 167 hours. The MIRI component required an additional 43 hours. These numbers sound abstractly large until you consider what they mean in practical terms. 210 hours of observing time on the most expensive, most technically demanding, most oversubscribed space telescope ever built, concentrated on a patch of sky approximately 1/35th of the area of the full moon, targeting a galaxy that initial screening had nearly dismissed as a foreground contaminant. The decision to invest that time, made through a competitive proposal process reviewed by panels of peer scientists, competing against thousands of equally compelling scientific programs from researchers across the world, reflects something about the culture of astronomical science that does not always receive adequate attention. It is not only the telescope's engineering that makes discoveries like this possible. It is the human infrastructure of scientific judgment, collaboration, peer review, and institutional risk tolerance that decides where the telescope points. Marcia Rike, Regents Professor of Astronomy and the principal investigator for the NIRCam instrument, the primary imaging camera through which most of Webb's galaxy science flows, had spent 17 years leading the NIRCam development program before launch. She was present during the integration and testing, during the cryogenic calibrations that verified the detectors would survive the temperature extremes of space, during the heart-stopping deployment sequence following Christmas Day 2021. The camera she led the development of, now operating at 37 Kelvin in the permanent shadow of a sunshield 1.5 million kilometers from Earth, had captured the images that enabled the detection of a galaxy from when the universe was 2% of its current age. This is what 17 years of engineering looks like when it works. There is a human story embedded in every great astronomical discovery, and it is almost always obscured by the language of papers and press releases, which emphasize the data and downplay the decades of patient, frequently frustrating labour that preceded it. The story of JWST 14.0 is also the story of the people who built the instruments that found it, who designed the survey that targeted it, who spent years writing proposal documentation and calibration reports and pipeline code, who argued in committee meetings for observing time allocations, who processed data at 2 a.m. and questioned their calibration choices and ran the analysis again when the first result looked too extreme to believe. It is the story of Jakob Helton discovering that a galaxy in the early universe had oxygen in it and sitting with the implications long enough to understand that it was not an error. It is the story of Kevin Hainline, not sleeping well, because the universe had turned out to contain more than the models had said it should, and the work of understanding what that meant was not yet finished. When Heinlein was asked, in a public statement released by the University of Arizona following the Nature Astronomy paper, how it felt to observe galaxies at the very edge of the observable universe, his answer was brief and honest in the way that good answers to hard questions usually are. "We're in an incredible time in astronomy history," he said. "We're able to understand galaxies that are well beyond anything humans have ever found and see them in many different ways and really understand them. That's really magic." He was right that it is magic. But the magic, in this case, comes with a cost. What Webb has found in the early universe is not just a record-breaking galaxy. It is a datum that sits in uncomfortable tension with the best models we have. And the discomfort does not diminish the wonder. It focuses it, because the question is no longer just, what is out there? The question is, what does it mean that it's there? And why didn't we see it coming? There is a principle in physics called theoretical conservatism, and it is both a virtue and a liability. The virtue, when a well-established theory makes a prediction that clashes with a new observation, the first and most responsible response is not to abandon the theory, but to look hard for errors in the observation, incomplete modelling in the analysis, or unaccounted systematic effects in the measurement chain. The liability, when theoretical conservatism is applied too long, it can delay the recognition of a genuinely new phenomenon by years or decades, as researchers spend their careers trying to reconcile an anomaly with a framework that cannot accommodate it, rather than building the framework that can. The history of cosmology is littered with examples of both. The discovery of the cosmic microwave background was initially resisted by steady-state cosmology's advocates, who generated increasingly contorted explanations for the 7 Kelvin microwave bath that permeates the sky before the evidence became overwhelming. The 1998 discovery of cosmic acceleration was doubted for years before the supernova data accumulated to the point of undeniability. Dark matter was proposed by Fritz Zwicky in 1933 to explain the anomalous velocities of galaxies in the Coma cluster, ignored for 4 decades and only fully accepted after Vera Rubin's galaxy rotation curve measurements in the 1970s made the case unavoidable. In each case, the anomaly preceded the acceptance by a substantial interval, and the length of that interval was largely determined by how deeply invested the theoretical community was in the model that the anomaly challenged. Webb is now, in mid-2026, approximately 4 years into its scientific operations. 4 years is a short time in the history of observational cosmology, not nearly long enough for the community to have reached consensus on what the anomalies mean. But it is long enough to say, with confidence, that the anomalies are not going away. They are accumulating. The little red dot crisis, in particular, deepened substantially through 2024 and into 2025, and it has a character that the early galaxy mass problem does not. These objects are not merely present in unexpected numbers. They appear to represent an entirely new category of astrophysical object that does not cleanly fit any existing classification. The initial discovery of the little red dots, announced in March 2024 from multiple independent survey programs, including the UN Cover Survey and the JWST survey, drew on NIRCam imaging that showed compact, point source-like objects with extraordinarily red colours in the near-infrared. Red in a way inconsistent with either normal stellar populations or standard active galactic nucleus emission at these redshifts. Spectroscopic follow-up, taken with NIRSpec, revealed broad hydrogen emission lines, the signatures of rapidly moving gas, with velocity widths of several thousand kilometers per second, implying virial black hole masses in the range of tens of millions to billions of solar masses. The overmassive nature of these black holes is not merely a curiosity, it is a fundamental challenge to the standard model of black hole growth. Under lambda CDM, supermassive black holes grow through a combination of gas accretion and mergers, the Eddington limit, the maximum rate at which a black hole can accrete without its own radiation blowing away the infalling material, places an upper bound on how quickly a black hole can grow, starting from a seed black hole of a few hundred solar masses, the expected product of the collapse of the first massive stars, and accreting at the Eddington limit continuously from the earliest cosmic epoch. A black hole can reach approximately 1 billion solar masses by a redshift of about 7, corresponding to a universe roughly 700 million years old. This calculation was already strained by the discovery of quasars at high redshift, and JWST has pushed the problem dramatically earlier. The broadline AGN discovered by Webb exist at redshifts between 4 and 9, and many of them host black holes that are hundreds of times more massive than their host galaxy's stellar population. This is the overmassive black hole problem, and it is structurally distinct from the galaxy mass problem because the two are pointing in opposite directions. The galaxy mass problem says there is too much stellar mass in the early universe. The overmassive black hole problem says the black holes have grown too fast relative to their host galaxies. In the local universe, these two quantities track each other tightly. In the early universe as observed by Webb, they have come apart. The black holes are ahead of the galaxies, dramatically so. Either the black holes grew first and the galaxies caught up later, or the standard picture of coevolution is wrong, or there is some third mechanism. Perhaps the little red dots are not simply active galactic nuclei, but something genuinely novel, that does not fit into either existing framework. In 2025, a remarkable paper from Penn State and the Max Planck Institute proposed exactly that third possibility. The black hole star hypothesis, named with a deliberate echo of the usual neutron star and black hole nomenclature, suggested that the little red dots are not galaxies with central black holes at all, but are instead a previously unrecognized type of object. Giant spheres of hot gas surrounding a massive black hole, puffed up by the black hole's own radiation into a quasi-stellar structure that mimics neither a normal galaxy nor a normal quasar. In this picture, the black hole has grown large enough that its radiation pressure supports an extended atmosphere of gas that it has not yet fully blown away, creating a compact, very red, very luminous structure that would appear in Webb's imaging as a small, intensely red dot. The ESA Webb team found what they described as the strongest evidence yet for black hole stars in early 2026, noting that several little red dots showed precisely the spectral and morphological characteristics that the black hole star model predicted. A broadline region consistent with gas, moving in the gravitational potential of a massive black hole, compact size, and a spectral energy distribution inconsistent with normal stellar populations or standard AGN emission. If black hole stars exist, and the evidence is suggestive enough that it warrants taking seriously, they represent the discovery of an entirely new class of astronomical object, one that was predicted theoretically decades ago as a possible phase in the early universe, but that had never been observationally confirmed. Their existence would have profound implications for the growth of supermassive black holes in the early universe, for the reionization of intergalactic hydrogen, and for the relationship between black hole growth and galaxy formation in the first billion years of cosmic time. But here is the problem that no single explanation for the little red dots can escape. Even if black hole stars account for some of them, they do not account for the early galaxy mass problem, the Hubble tension, or the DESI dark energy anomaly. These are independent datasets, pointing toward the same general region of scientific discomfort. And the disturbing possibility, the one that lives, unspoken, in the margins of the papers and the discussions at conferences, is that all of these anomalies share a common root, that what Webb is exposing is not a collection of isolated puzzles but a systemic failure of the standard model to describe the early universe correctly. The Hubble tension, in this light, is particularly telling because it is not merely a discrepancy between two measurements. It is a discrepancy between the early and late universe, between what the physics of 380,000 years after the Big Bang predicts for the present-day expansion rate and what the present-day expansion rate actually is. The early universe, as measured by Planck's CMB observations, is consistent and precise. The late universe, as measured by every independent distance ladder approach, consistently returns a higher value. The gap between them implies that something happened between the recombination epoch and today that changed the expansion history in a way that the standard model did not predict. One of the most actively explored modifications to the standard model to address this is called early dark energy, a form of dark energy that was more important at early times than it is today, contributing additional expansion energy in the epoch before recombination, and thereby increasing the inferred expansion rate at that time. By increasing the effective Hubble constant in the pre-recombination epoch, early dark energy models can in principle shift the CMB-derived H0 prediction upward toward the locally measured value. This is not a trivial modification. It changes the thermal history of the universe, the growth of structure, and the matter-power spectrum in ways that must simultaneously be consistent with all other cosmological observations. The constraints are tight, but several early dark energy models remain viable as of mid-2026, and Webb's ongoing measurements, particularly its photometric and spectroscopic surveys of the galaxy population at redshifts between 4 and 15, are providing new tests of the structure growth predictions that these models make. The stakes of getting this right cannot be overstated. The Hubble constant determines the age of the universe. The current best estimate, under lambda CDM with the Planck CMB value, is 13.8 billion years. If the local measurement of H0 73 km SOP-P is correct, and the CMB-derived value is the one that needs revision, implying that the standard model is wrong at early times, then the age and expansion history of the universe need to be recalculated. Not by much, perhaps, but the recalculation would propagate through every quantity derived from them: the inferred masses of galaxy clusters, the distances to Type Ia supernovae, the predictions for the future fate of the cosmos. The universe we thought we lived in, and the universe we actually live in, would by some measure be different things. And beyond even the Hubble tension, the DESI results on dark energy evolution carry stakes of their own. If dark energy is evolving, if the cosmological constant is not in fact a constant, then it cannot be the zero-point energy of the quantum vacuum, which has a fixed density independent of the scale factor. This would close one major theoretical door and open several others. It would suggest that dark energy is instead a dynamical field, a quintessence field, in the language of the theoretical literature, with its own equation of motion, its own potential energy landscape, and its own evolution through cosmic time. The properties of that field would need to be determined, its ultimate fate, whether it eventually decays to zero, leaving the universe in a state of matter-dominated deceleration, or grows unbounded, eventually tearing apart not just galaxies but atoms in a scenario cosmologists call the Big Rip, would need to be computed, and the observational requirements for determining those properties would drive the design of the next generation of cosmic surveys, potentially reshaping the field for a century. This is not a contained scientific problem. It is a question about the nature of space-time itself. It would be dishonest, and ultimately unproductive, to write about Webb's challenges to cosmology without spending serious time on the counter-arguments, the cautions, and the many places where the alarmist narrative has outrun the evidence. Science journalism, and science communication more generally, has a structural bias toward the narrative of crisis and revolution. Standard model confirmed to additional decimal place is not a headline that attracts readership. Webb breaks cosmology is, and in the first 2 years of Webb's science operations, the latter framing dominated public discourse in ways that did not always accurately represent the measured, qualified position of the expert community. Let us be precise about what Webb has and has not established. The galaxy formation tension is real, but has been substantially reduced from the most alarming early reports. The initial photometric analyses, published in preprints throughout 2022, estimated stellar masses for early galaxies using SED fitting techniques that, it later emerged, were not fully accounting for the contribution of nebular emission, particularly from ionized gas in star-forming regions, to the broadband photometric flux. When a galaxy is undergoing intense star formation, the ultraviolet and optical emission from hot young stars ionizes the surrounding gas, which then produces continuum and line emission that adds to the apparent stellar continuum. If this emission is not properly modelled, the inferred stellar mass is overestimated, because the models try to account for the excess brightness with more stars, rather than with gas emission. The ANIA-SPEC spectroscopic data, which became available in quantity from the second year of operations onward, enabled much more constrained SED modelling, and several of the most extreme photometric mass estimates were revised downward. The NASA summary paper from 2025, Webb finds early galaxies weren't too big for their britches after all, made this point with a directness that some in the community found welcome and others found somewhat overstated in the other direction. The paper's finding that revised spectroscopic masses brought many early galaxies back within the lambda CDM prediction interval was legitimate, but the prediction interval within which they now fit is not the narrow interval of the model's most confident predictions. It is the broader interval that includes the most optimistic assumptions about star formation efficiency, allowing efficiencies close to the theoretical maximum. Lambda CDM with 100% star formation efficiency is not quite the same theory as lambda CDM with the few percent efficiencies that physical reasoning and lower redshift observations support. The model is accommodating the data, but it is doing so at the cost of substantial flexibility in its baryonic physics assumptions. That accommodation is scientifically legitimate. It is also, at some level, a concession that the model needs better physics. Furthermore, and this is the point that the no-tension papers most often elide, JWST GSZ 14.0 is not well explained by better nebula emission modelling. Its oxygen abundance is not a nebula emission artifact. The ALMA detection of 88 micrometers in this galaxy, confirmed independently of the MIRI detection, establishes the presence of heavy elements through a completely different observational technique. The galaxy existed, was chemically evolved, and had a half-light radius of 260 parsecs in a universe 290 million years old. These facts are not contested by any analysis, however conservative. What they mean, what revisions to theory they require, is contested. But the facts themselves are robust. On the Hubble tension, the situation as of mid-2026 is equally nuanced. The December 2024 Webb study that measured the Hubble constant using type supernovae and Webb recalibrated Cepheid distances returned H072, 6 km/s MOP, virtually identical to the Rias group's long-standing value. The conclusion: Cepheid crowding effects in Hubble data were not responsible for the high local H0 because correcting for them with Webb's superior resolution and infrared sensitivity did not change the answer. The tension with the Planck CMB value persists. The Friedman group's alternative analysis, using the tip of the red giant branch as a distance indicator rather than Cepheids, returned a value closer to 70 km/s, intermediate between the two camps. But this intermediate value, while superficially reassuring, does not resolve the physics. A true H0 of 70 km/s MOP-P would still be in tension with the Planck value of 67.4 at approximately 2 sigma reduced tension but not zero tension, and the question of which distance indicator is more reliable, Cepheids or the tip of the red giant branch, has its own complexities. Both techniques involve calibration chains with multiple steps, each of which introduces uncertainties that can accumulate in non-trivial ways. A May 2025 combined Webb and Hubble study returned H0 70.4 km/s SPC with a 3% uncertainty, again intermediate, again not definitively resolving anything. The statistical landscape of the Hubble tension as of mid-2026 looks like this. The tension between the CMB-derived value and the Cepheid-based local value remains at approximately 4, 5 to 5 sigma in the most careful analyses. no systematic error has been identified that explains it. The tension between the CMB value and the TRGB-based local value is approximately 2 sigma. The tension between the CMB value and other independent local probes, strong gravitational lensing time delays, gravitational wave standard sirens, surface brightness fluctuations, ranges from approximately 2 to 4 sigma. No single method agrees with the Planck value. They all sit above it. The probability of this pattern arising from a coincidental collection of independent systematic errors, all biasing in the same direction, is very low. The tension is real. What could resolve it? In principle, 3 things. First, a systematic error in the Planck CMB analysis, perhaps in the modelling of foreground dust emission or in the treatment of small-scale power in the temperature anisotropy spectrum. This possibility has not been fully excluded, but after years of scrutiny from multiple independent groups, no such error has been found. Second, a systematic error in the local distance ladder, perhaps in the metallicity calibration of Cepheids, the treatment of reddening by dust, or the anchoring of the distance scale to geometric parallax measurements. Webb has reduced but not eliminated this possibility. Third, new physics beyond lambda CDM, early dark energy, modifications to the pre-recombination expansion history, new neutrino physics, or other extensions of the standard model that alter the CMB-derived H0 prediction without disturbing the model's other successes. The third option is increasingly the working hypothesis of a significant fraction of the theoretical community. A 2025 paper in the monthly notices of the Royal Astronomical Society attempted to construct a unified solution to the Hubble tension and the early galaxy formation puzzles using a modified cosmological model with covarying coupling constants, a framework in which the fundamental constants of nature are not truly constant but vary with the state of the universe over cosmic time. The paper found that this model could simultaneously address both the early galaxy mass excess and the Hubble tension without violating existing constraints from Big Bang nucleosynthesis or CMB physics. It was a minority view, strongly contested, and explicitly preliminary, but it represented exactly the kind of theoretical exploration that a data anomaly of this magnitude and persistence demands. The little red dots present their own complicating layer of nuance. By mid-2025, the consensus had solidified that many, perhaps most, of the little red dots are active galactic nuclei, systems in which a massive black hole is actively accreting gas and producing the broad emission lines that characterize them. The question is what kind of active galactic nucleus they represent and why they do not match the properties of any known AGN population at lower redshift. A Nature paper in 2025 confirmed, using combined JWST and X-ray data, that the little red dots show extremely weak X-ray and radio emission relative to their UV and optical brightness, the opposite of what standard AGN models predict. A typical AGN at these luminosities would be X-ray bright. The little red dots are X-ray quiet to a degree that conventional models struggle to explain. The most widely discussed resolution to the X-ray quiet problem in 2025 was the hypothesis of very high column densities of gas and dust surrounding the central black hole, absorbing the X-rays before they escape while allowing the longer wavelength UV and optical emission to penetrate. This Compton-thick absorption model is not physically implausible in the dense gas environments expected in the early universe. But several X-ray observatories have obtained deep exposures of fields containing little red dots and found that even correcting for expected absorption, the X-ray emission is fainter than expected by factors of 10 to 100. The absorption hypothesis strains at its limits. The black hole star model from Penn State and Max Planck, which gained observational support from the ESA Webb team in early 2026, offers a different resolution. If the central object is surrounded by a large sphere of optically thick gas supported by radiation pressure, the atmosphere of the black hole star, then X-rays produced near the black hole would be thermalized within this gas, re-emerging as lower energy optical and infrared photons rather than as X-rays. The spectral energy distribution of a black hole star would peak in the optical and near-infrared, with very little emission at X-ray wavelengths. This matches what is observed in the little red dots. The model also predicts that these objects should be compact, roughly the size of the radiation pressure-supported atmosphere, which matches the observed compactness. And it predicts that they should be relatively common in the early universe, when gas densities were highest, becoming rare at lower redshifts as gas densities fell. This too matches the redshift distribution of the little red dot population. The black hole star model, if confirmed, would be one of the most significant discoveries of Webb's operational period. Not because it resolves the tension with lambda CDM, it doesn't, directly, but because it would represent the observational discovery of an entirely new class of astronomical object, one that bridges the theoretical gap between the seeds of the first black holes and the fully formed supermassive black holes seen in high redshift quasars. It would explain how black holes grew to billions of solar masses in the first billion years of cosmic time without requiring continuous Eddington limit accretion. The black hole star phase could allow rapid mass growth through a different mechanism, one that does not saturate the standard feedback limits. And it would suggest that the early universe was populated by a class of objects that look like neither galaxies nor quasars, but something else entirely, something that pre-Webb cosmology had no framework to anticipate or categorize. Beyond the specific anomalies, there is a broader structural issue with the standard model that Webb is beginning to expose, one that is less dramatic in its individual manifestations, but more fundamental in its implications. Lambda CDM is, at its core, a model of the dark sector, of dark matter and dark energy. Its predictions for the visible universe depend on coupling the dark sector to baryonic physics through a set of subgrid models, prescriptions for how gas cooling, star formation, stellar feedback, and black hole growth work at scales below the resolution of cosmological simulations. These prescriptions are empirically calibrated to match low redshift observations. They are not derived from first principles. They are, in a meaningful sense, tuning parameters that absorb the complexity of physical processes that are too small scale to simulate directly. Webb is now providing data from an epoch, the first billion years, where these tuning parameters have never been calibrated. The early universe is not just a more distant version of the universe at lower redshift. It is a physically different environment. Higher density, higher temperature, higher gas fractions, different metallicities, different radiation fields. The feedback processes that govern galaxy formation in the nearby universe operated in an entirely different regime in the first billion years. And the evidence from JWST GSZ 14.0 and the other anomalous early galaxies is not just that there is more stellar mass than expected, it is that the chemical enrichment happened faster, the galaxies assembled earlier, the star formation was more efficient, and the black holes grew more rapidly than any calibration of the standard baryonic physics prescriptions predicted. This does not mean lambda CDM is wrong. It means that our model of the baryonic processes within lambda CDM is wrong, at least in the early universe regime. The question is whether correcting those baryonic physics models, improving the treatment of stellar feedback, gas cooling, AGN feedback, and star formation efficiency in the early universe, is sufficient to bring the model back into agreement with Webb's observations, or whether doing so will expose deeper tensions that require revisions to the dark sector itself. As of mid-2026, the community is split approximately into thirds. Roughly a third believes that improved baryonic physics alone will resolve the tension. Roughly a third believes that the Hubble tension and the early galaxy anomalies together require some modification to the dark sector, most likely involving a non-constant dark energy equation of state or some form of early dark energy. And roughly a third are genuinely agnostic, convinced that the data from Webb are not yet sufficient to discriminate between these options, and that the field needs more observing time, more spectroscopic confirmation, and more sophisticated analysis tools before reaching any conclusion. This is not confusion. This is science operating exactly as it should in the face of genuinely new data. The disagreement among experts is not a failure of the scientific process. It is the process. It is the mechanism by which observational anomalies are subjected to maximum scrutiny before they force theoretical revision. The revision, when it comes, will be better for having been stress-tested by every alternative explanation that 3,000 cosmologists could collectively devise. What is clear, however, is this. The universe that Webb has begun to reveal is more complex, more structured at early times, more chemically evolved in its infancy, and more varied in its populations of objects than any model in existence predicted, whatever the final accounting of that complexity turns out to be. Whether it traces to baryonic physics, to dark energy evolution, to black hole stars, or to some theoretical framework not yet written, the version of cosmology that emerges from the Webb era will be richer and more accurate than the one that preceded it. And the anomalies, however eventually explained, will have played the essential role that anomalies always play in the history of science. They force the question that the comfortable theory had never had to answer. There is a patch of sky above the constellation Fornax, roughly the apparent size of a grain of sand held at arm's length. In 1995, Hubble looked there and found 3,000 galaxies. In July 2025, Webb returned to the same coordinates, the Hubble Ultra Deep Field, and recorded what is now one of the deepest infrared images ever obtained of the extragalactic universe. Over 500 galaxies resolved in a field that Hubble had known for 3 decades, but transformed. Objects that were unresolved smears in Hubble's deepest images are now resolved into structures. Morphology visible, colour gradients measurable, companion galaxies separated from hosts. And at the very edge of Webb's sensitivity, at redshifts that Hubble could not reach, new objects appear, faint, red, compact, at the limit of the instrument's capability. Some of them are JWST 14-0's cousins, bright galaxies in the early universe, formed in the first few 100 million years after the Big Bang, waiting to be confirmed, analysed, and incorporated into the ever-evolving account of how the cosmos assembled itself from nothing into the structured, luminous, chemically rich universe we inhabit. The next decade of Webb science will not be a continuation of discovery at the current pace. It will accelerate. Webb's initial years have been dominated by the dramatic, headline-generating discoveries, the record-breaking galaxies, the little red dots, the Hubble tension confirmation. The next phase will be characterized by the patient cumulative work of statistical analysis, building samples of thousands of spectroscopically confirmed high redshift galaxies, measuring their stellar masses, star formation histories, chemical abundances, and black hole properties with precision sufficient to distinguish between the competing theoretical explanations currently on the table. Several major observing programs are designed for exactly this purpose. The JWST collaboration is continuing to build out its spectroscopic catalogue, targeting not just the highest redshift candidates but the full population of galaxies between redshift 3 and 15, the full sweep of cosmic noon to cosmic dawn, with NIRSpec multi-object spectroscopy. The SEERS program, the Cosmos Web Survey, and the Primer Survey are mapping progressively larger areas of sky at Webb's sensitivity, building the statistical samples needed to determine whether the anomalous galaxy number counts are representative of the full sky or are driven by cosmic variance, the natural fluctuation in galaxy density from one region of the universe to another. The Atmospheric Characterization Program, Webb's campaign of transmission spectroscopy of exoplanet atmospheres, is proceeding in parallel with the cosmological work, and while it belongs to a different domain of astrophysics, its implications are connected to the same fundamental question. If the early universe was more chemically complex than expected, if heavy elements accumulated faster in early galaxies than the models predicted, then the raw ingredients for planetary systems, for silicon, carbon, oxygen, iron, were available earlier in cosmic history than we thought. The chemistry of planetary atmospheres that Webb is now beginning to measure in nearby stellar systems is the downstream product of a chemical enrichment history that the telescope is also characterizing at the other end of the cosmic timeline. The two programs speak to each other across 13 billion years of cosmic evolution. The TRAPPIST-1 system, 7 Earth-sized rocky planets orbiting a nearby red dwarf star at a distance of 47 light-years, has been one of Webb's primary atmospheric targets. The results so far have been definitive in one direction and inconclusive in another. TRAPPIST-1b, the innermost planet, shows no evidence of a thick carbon dioxide atmosphere. It appears to be a bare rock, its dayside heat radiating directly into space without the insulating blanket of a substantial atmosphere. TRAPPIST-1c, slightly further out, also shows no evidence of a thick CO2 atmosphere. But TRAPPIST-1e in the habitable zone is still under active investigation, and the measurements Webb is accumulating there, constraining the atmospheric composition, the surface temperature, and the albedo, are building toward a determination of whether any of the TRAPPIST-1 planets retain the conditions for liquid surface water. This is not a peripheral concern. It is the deepest question that any telescope has ever been positioned to address. The Euclid Space Telescope, launched in July 2023, has been conducting a wide-field survey of the geometry of the universe complementary to Webb's deep-field work. Euclid's primary scientific goal is to map the dark matter distribution and dark energy equation of state through weak gravitational lensing and baryon acoustic oscillations across a survey area of 14 square degrees, roughly a third of the entire sky. The first Euclid data releases, arriving in 2025, are already providing constraints on the dark energy equation of state that will complement the DESI results. When the full Euclid survey is complete, its combined analysis with DESI and with Webb's galaxy formation measurements will provide the most comprehensive test yet of whether dark energy is constant or evolving, and whether the Hubble tension can be accommodated within a modified cosmological model or requires entirely new physics. The Roman Space Telescope, NASA's Wide Field Infrared Survey mission, scheduled for launch in the late 2020s, will amplify Webb's discovery space by orders of magnitude in survey area. Webb can observe a patch of sky the size of a grain of sand held at arm's length with extraordinary sensitivity. Roman's 2.4-metre mirror, paired with a 300 megapixel detector array covering a 28 square degree field of view, will survey regions hundreds of times larger. Roman will find millions of galaxies at high redshift, not the hundreds or thousands of spectroscopically confirmed objects that JWST currently holds, but statistical samples large enough to definitively measure the galaxy luminosity function, the star formation rate density, and the AGN population over the full sweep of cosmic history. If the little red dot population follows the distribution implied by current Webb data, Roman will find hundreds of thousands of them, enough to map their spatial clustering, determine whether they trace the cosmic web of dark matter halos, and measure their evolution as a function of cosmic epoch. It will turn a puzzle into a census. On the theoretical side, the next decade will see the deployment of progressively more sophisticated cosmological simulations capable of incorporating the Webb error constraints. The Illustris TNG and E-Eagle simulation families have already been extended to higher resolution and earlier cosmic times, attempting to reproduce the galaxy populations that Webb is finding. The next generation of simulations, including projects like Flamingo and Millennium TNG, incorporate larger volumes with higher resolution, improved treatment of black hole feedback, and more physically motivated star formation models. These simulations are being run explicitly to test whether lambda CDM, with improved baryonic physics, can reproduce the Webb observations, or whether the parameter space required to do so is so far outside physically motivated expectations that new cosmological physics becomes unavoidable. The answer to that question will come through a combination of theoretical effort and observational evidence that cannot be rushed. Good science, unlike good narrative, does not have a fixed timeline for its resolution. The anomalies that Webb has uncovered may be explained within the current framework by 2030, or they may persist and sharpen until they force a paradigm shift that remakes cosmology. Both outcomes are possible, both have historical precedent. What is certain is this: the patch of sky above the constellation Fornax, the grain of sand at arm's length, has been looked at more carefully than any comparable region of the universe in the history of human observation. In 1995, we found 3,000 galaxies there. In 2025, we found them resolved into structure, embedded in chemical histories, accompanied by objects that fit no prior category. In 2045 or 2065, astronomers using telescopes not yet designed, analysing data from surveys not yet begun, will look at this same region of sky, or more probably at regions far deeper and far wider, and read in the light of the most distant galaxies a story about the beginning of time that is more complete, more accurate, and more unsettling than anything we can currently imagine. They will see what we have missed, they will correct what we have gotten wrong, and the questions that Webb has opened, questions about the speed of the universe's expansion, about the nature of dark energy, about how quickly the first structures formed from the primordial dark, will still be questions, refined and sharpened, handed forward. This is the nature of the horizon. It recedes as you approach it. That is not a failure of the science. That is what it looks like when the science is working. There is something specific about the quality of light from the most distant galaxies that I keep returning to. Not the physics of it, not the redshift, not the spectral lines, but the simple fact of its age. When the photons that formed the image of JWST 14.0 on Webb's detector array arrived at that detector after a journey of 13.5 billion years, the star that emitted them had already been dead for longer than the Earth has existed. The galaxy that contained that star had already evolved through multiple phases of its history. The oxygen atoms that MIRI detected in its gas clouds had already been inside stars, exploded out of stars, floated through interstellar space, been incorporated into the next generation of gas clouds, and set off on their 5 billion year journey before the solar system existed. We did not observe that galaxy. We observed its past. We are, every one of us who has looked at an image from the JWST campaign, looking at a time machine, not a metaphorical one, not a poetic one, but a literal physical consequence of the finite speed of light and the vastness of the universe. The telescope is not a device for seeing far away, it is a device for seeing far back. Every additional billion light years of depth is another billion years of cosmic history, and Webb's ability to see clearly at 5 billion light years, means that we are now reading the opening pages of the universe with something close to actual legibility, rather than the blurred impressions that were all we had before. What we are reading on those pages is a story that does not match the one we thought we knew. The universe was not the quiet, slowly assembling place that our models described. It was turbulent, productive, chemically active almost from the start. It formed galaxies faster than our equations said it could. It built black holes heavier than the timescales allowed. It scattered heavy elements into its intergalactic spaces before the first generation of stars should even have finished their lives. It is a universe that seems, on every observational front, to be more in a hurry than our physics predicted, as though the cosmos had an urgency about the business of becoming that no model quite captured. This urgency is, I think, one of the most profound things that Webb has given us. Not a specific measurement, not a specific discovery, but a revised sense of the texture of cosmic history. The universe is not a patient assembler. It is, or at least it was, a rapid, almost violent constructor of complexity, building structure from uniformity in what, by cosmic timescales, amounts to an eye blink. The fact that galaxies with stellar masses of hundreds of millions of solar masses, containing oxygen produced by multiple generations of stellar evolution, existed only 290 million years after the Big Bang, means that the work of making the universe complex, making it the kind of place where life is chemically possible, began almost before the universe had finished setting its initial conditions. There is a connection between that fact and the question of our own existence that I find impossible to ignore. If the early universe assembled chemical complexity faster than we thought, if oxygen, carbon, and the other heavy elements were distributed through the interstellar medium on timescales shorter than any model predicted, then the window during which life could potentially emerge, anywhere in the universe, opens earlier than we believed, not by a little. The difference between the first potentially habitable planetary systems could have formed 5 billion years after the Big Bang, and the first potentially habitable planetary systems could have formed 1 or 2 billion years after the Big Bang, is, in its implications for the question of cosmic loneliness, enormous. It means that there is potentially far more time and far more chemical substrate for life than we had calculated. It means that if we are alone in a universe that gave life every opportunity, which makes the aloneness, if real, considerably more haunting. But we do not know that we are alone, and in the same way that the early universe's faster-than-predicted chemistry suggests that the ingredients for life were distributed earlier than we thought, the exoplanet atmospheric surveys that Webb is simultaneously conducting are beginning to characterize the actual conditions on rocky planets in the habitable zones of nearby stars. The two programs, the Deep Cosmological Survey and the Nearby Exoplanet Characterization, are different faces of the same inquiry. One asks how the universe made the ingredients, the other asks whether the ingredients are anywhere in use. Neither question has an answer yet. Both questions are being pursued with instruments of unprecedented capability, in a scientific era of unprecedented ambition, by researchers of uncommon dedication and skill. The answers, if and when they come, will be the most consequential findings in the history of human inquiry. And they may not come as singular moments of revelation. They may come the way most of the best science comes, gradually, cumulatively, as evidence accumulates from multiple observations, as consensus builds slowly among competing interpretations, as the anomaly that nobody could explain becomes the explained phenomenon that nobody can imagine having not known. The James Webb Space Telescope has been operating, as of this writing, for approximately 4 years. Its designed lifetime is 10 years, potentially extendable beyond that depending on fuel reserves. The fuel budget, the small amount of hydrazine propellant used for orbit maintenance at L2, was so precisely conserved during the Ariane 5 launch in December 2021 that the mission planning team subsequently revised the telescope's operational lifetime estimate upward, from a minimum of 10 years to potentially 20 or more. 20 years of Webb, 20 years of the deepest infrared observations in human history, 20 years of galaxy spectra, exoplanet atmospheres, stellar nurseries, and objects that fit no existing category. 20 years of anomalies that challenge the standard model, followed by theoretical revisions that explain the anomalies, followed by new observations that challenge the revised model, in the self-correcting iterative spiral. That is what science actually looks like from the inside. We are, in other words, very much at the beginning. The grain of sand above Fornax has been examined more carefully than ever before, and it has returned data that breaks every theory we had. That breaking is not the end of understanding. It is the condition for understanding at a greater depth. The universe, as it turns out, is not obligated to be simple. It is not required to fit the first framework we built to describe it. It is required only to be itself. And when we build instruments capable of seeing it clearly enough, it reveals exactly that, itself in its full disruptive, profligate, mind-boggling complexity. There is still the question of what the little red dots are. There is still the question of why the universe is expanding faster than its own early history predicts. There is still the question of how galaxies the size of our own Milky Way assembled themselves in a universe barely 290 million years old, and how they managed to do it while producing oxygen, and what that means for the timeline of everything that followed, including us. Science does not always give us endings. Sometimes it gives us horizons. And perhaps that is the point, not to arrive, but to keep the question alive long enough for someone younger, braver, and equipped with a better telescope to carry it further than we could reach. We are the generation that built Webb. We are the generation that asked. The answers, the full answers, belong to whoever comes next.